Good afternoon. Thank you for attending today's SBCA webinar, Understanding Truss Design Drawings, Part 2. This is the 9th in a series of webinars aimed at informing building designers, whether they are architects, engineers, or others in the design community, on aspects of the component manufacturing industry. The goal of this series is to provide structural component design guidance, as well as provide perspectives on what today's component manufacturing industry is capable of, and also explore how our industry can be an effective partner with building designers in ways that will make their lives easier and/or make them heroes in the eyes of their customers. In this presentation, we're going to finish our deep dive into truss design drawings, or TDDs, which are an essential design document in the construction of a building. Because the audience for any one of these presentations may include design professionals from different disciplines with varying levels of experience and who work primarily with anything from single-family, multifamily, or light commercial projects, most of my observations today will remain at the 30,000-foot view. My name is Sean Shields. I'm the Director of Marketing at SBCA. I've been with the association for over 20 years and will be bringing to bear my experience talking with component manufacturers across the United States throughout this presentation. Here's a brief summary of what we'll cover today. I'll start by providing a brief overview of SBCA and its role in the component manufacturing industry. For those of you who have attended other presentations in this series, I apologize, this will be repetitive, but I want to make sure for anyone who is new that I give you a sense for the size of the component manufacturing industry, as well as a good understanding of the role that SBCA plays within the industry. In part one of this presentation, I went through various elements of the graphical elements of a truss design drawing, and I'll spend just a few moments reiterating a few key points before we get into the meat of today's presentation, which will be looking at the data contained at the bottom portion of the truss design drawing and talking about what many of those data points mean. In this bottom portion of the truss design drawing, we'll be looking at everything today from load duration factors and deflection to lumber and bracing. Finally, I'll conclude with some observations on how a component manufacturer can be a valuable resource to building designers in the building design process. Now, SBCA is the premier trade association for the structural building components industry in North America. With over 40 years of history, SBCA has developed an extensive network that enables it to reach the entire length and breadth of this unique portion of the construction industry. SBCA has a strong tradition of providing sound engineering and fabrication guidance to its members to help promote their growth and success in the marketplace. But as the market has matured, its primary focus has shifted to helping build connections between companies and individuals throughout the industry, whether they happen to be in the same local market or they're spread across the continent. These relationships are built through both face-to-face events, virtual events online, and digital communications. SBCA's premier face-to-face event is the annual Building Component Manufacturers Conference, or BCMC, which is traditionally held in the fall. This year, it will be held in Omaha, Nebraska. BCMC brings thousands of component manufacturers and suppliers together for an entire week of intense networking, idea sharing, and business transactions. In addition to the BCMC show, SBCA hosts 3 additional face-to-face meetings throughout the year called Open Quarterly Meetings, or OQMs. These meetings are held across the country and offer anyone a more intimate opportunity to build relationships with some of the largest and most forward-thinking component manufacturers in the industry. Finally, SBCA has developed an extensive suite of tools and resources for today's manufacturer that range from digital quality management software to an extensive library of online training modules. Just to give you a sense for how large SBCA's membership is, this map is a scatter plot of the over 1,300 component manufacturing facilities in the United States today. Of those dots, 907 of them belong to SBCA member companies. As you can see, these facilities reach every community in the country, allowing builders to use these products in any project, no matter where that project is located. To give you a sense of scale, SBCA member facilities sold approximately $9.12 billion in product in 2023, out of an estimated total of $9.31 billion. Lastly, SBCA is an inclusive organization, and we welcome everyone engaged in the light frame construction industry to get tied into our extensive network of structural component manufacturers and their supply chain. There's an infinite number of opportunities for individuals to get involved, meet manufacturers, share ideas, solve problems, receive and offer education, and most importantly, build meaningful business relationships that can transform the way anyone approaches their job and positively alter the trajectory of their business and career. Now, before we get into the truss design drawings themselves, I do want to reiterate that each truss design drawing is generated through a proprietary piece of design software. Today, there are 4 companies that supply truss design software and metal connector plates to this $9 billion industry. Those companies are MyTech, a Berkshire Hathaway company, Alpine, an ITW company, Simpson Strong-Tie, and Eagle Metal Products. Every single component manufacturer in the United States uses one of these 4 companies and their software suites to develop truss designs today. And while truss design drawings, which is pictured here, here's an example, are largely standardized, each software of those 4 organizes the truss design drawing output from their software a little bit differently. So just to give you a sense, here would be a different output. And today, as we're going through some of the different elements of the lower portion of the truss design drawing, you'll see some of the differences, and we'll compare and contrast them, just so that you get a sense for how information might be output a little bit differently, or where it may be located in a slightly different place. Now, as we discussed in part 1, the top half of the truss design drawing provides a graphical representation of the truss, and it identifies a number of key elements to help everyone from production workers and installers to building designers and building inspectors quickly identify aspects of a truss important to their role in the process. For example, a production worker can quickly look at the graphical representation and have a good sense for the size and scope of a particular truss. Again, the installer will be looking at other pieces of information in the graphical portion of the TDD. But, at the top, you will normally see a truss tag. And then you will see something called out that will label the truss type. Beyond that, you'll have the quantity of trusses in that particular job that carry that truss tag. And then you will also have an area that will list the number of plies in that truss. This is typically 1, unless it's a multi-ply girder truss. Below that, you'll see the shape of the truss itself. It will also give you key measurements, like the length of each panel point in the truss, as well as, of course, the overall span between the bearing locations. It will also call out the pitch of the truss along the top chord. We'll also call out all the locations of the truss joints. And you will also see the size of the plates at each one of those joints, along with the orientation of each plate. You'll also see the location of the top chords, of course, the bottom chords, and of course, the webs within the chords. Okay, so that's the highlight of what we covered in part 1. Go so fast. But as we get into part 2, we're going to look at we're going to start with one key data point contained in the bottom half of the truss design drawing, which addresses truss spacing. Now, for most residential and light commercial application, truss spacing is 2 feet on center. Typically, the component manufacturer will work with the customer to determine their desired truss spacing. Again, this is typically 2 feet on center, but for, let's say, agricultural applications like post-frame construction, trusses may be spaced anywhere from 4 feet to 16 feet on center. Sometimes, if it's anticipated, there will be something like slate or concrete tiles on the roof. So again, very heavy dead loads. The roof trusses may be spaced 12 inches or 16 inches on center instead of 24. Similarly, floor trusses can be spaced 12 inches or sometimes 19.2 inches on center instead of 24 inches on center when the building designer wants to achieve, let's say, a longer span at a given floor depth, or if they want to control for something like floor stiffness. Now, while theoretically the truss spacing can be any distance at all, the measurements I mentioned specifically are typically used to allow for the most efficient application of today's standard sheathing products that measure 4 feet by 8 feet. This, of course, allows the seams between individual sheets to line up over the center of each truss. So here's looking at a truss design drawing. One other important detail as I get into this that I covered in part 1 of this presentation that I think is going to be pertinent as we look at these lower sections of the truss design drawing is that all measurements on the TDD are listed in 3 separate numbers. So if you draw your attention to the bottom here, which has, again, the panel measurements and then the overall span of the truss between the bearing locations. The first number will always be listed in feet. The second number will always be listed in inches. And then that third number is 1/16 of an inch. Again, the reason for this approach is to allow for quick calculations without requiring decimals or complicated fractions. And this conversion to this nomenclature eased the early transition from paper and pencil designs to a digital format. Again, I'm just going to reiterate this one last time as we start getting into comparing and contrasting. While the information contained in a truss design drawing is largely standardized, both by the requirements of the building code and TPI-1, each proprietary design software will display some of this information slightly differently. So here's a good example with truss spacing. As you can see here, this truss design drawing output lists the truss spacing at the top of the second column. You can see here, under the, just under the graphical portion of the truss design drawing. However, if we look at a different truss design drawing, you'll see that the spacing is called out at the bottom of the first column under the graphical portion. You also notice that in this output, the distances drop that third measurement of 1/16 of an inch if that measurement is 0. Okay, so after truss spacing, the next thing to check on is the loading conditions of the truss. These are the design criteria the truss designer inputs into the design software ahead of time, based on a wide variety of inputs from anything like the applicable building codes, so the IBC or the IRC. It may include their specific manufacturer's design criteria, which may vary widely from the SKUs of lumber that they carry or the truss plates that they have, or any other considerations that they may impose. And of course, there may be potential preferences of the builder or customer. And of course, there's also all the information contained on the building plans themselves. So when looking at loading, typically the first thing that you would see on a truss design drawing are live and dead load assumptions for the truss. So live loads are those that are anticipated to change over time, whether that's people walking on the roof or floor, whether it's snow or rain loads, anything like that. Conversely, dead loads are those that are considered static over the life of the truss. This is typically things like sheathing or exterior cladding. Again, you might see this number go higher if the roofing material is assumed to be heavier, like, again, concrete or slate on the roof, or sometimes with floor trusses, they know that they're going to have stone tile on a kitchen floor. You may also see higher numbers if there are known design elements like solar panels on the roof or a kitchen island on a floor system. So looking at the truss design drawing, The first thing you'll see are TCLL, which stands for top chord live load, and TCDL, which is the top chord dead load. Again, the same nomenclature is used for the bottom chord with the BCLL and BCDL. Now, the top chord live load will typically be higher than the dead load. Again, think of snow versus, and the weight of snow versus sheathing and shingles. For the bottom chord, the dead load will similarly be low to accommodate something like ceiling gypsum, but the bottom chord live load will typically be 0. This will definitely change if an area within the truss is designed for storage or even a living area. This is typical of attic trusses, as an example. And as you look at this truss design drawing, you can see that there is an asterisk after the 0.0 for that bottom chord live load. And if you follow that asterisk down into the notes, you'll see that the note indicates this truss has been designed for a live load of 20 PSF on the bottom chord in all areas where a rectangle 3 feet 6 inches tall by 1 foot wide will fit between the bottom chords and any other member. And then, of course, there's that note continues that the bottom chord dead load remains at 10 PSF. So again, there's accommodation that if in the design of the roof system, there is an area where there may be some possibility for live load, then it's designed for 20 PSF. The next thing to look at is the load duration factors, or LDFs, used in the design of the truss. Load duration factors are used in truss design to account for the effect of a given design load's duration on the strength of a structure. So the reason why this is done is because wood has the ability to handle higher stresses under shorter periods of time. Now, again, I don't want to get too much into the weeds on this. You can write very long, engineering-based white papers on just one of these LDFs. But on a basic level, design loads are classified by how long they are expected to act over the life of the structure. So for example, an LDF of 10 years is considered normal loading. So the LDF is 1.0 and neither increases nor decreases allowable stress when designing a truss. But in contrast, a 2-month load duration is usually applied when considering snow loads, and that has an LDF of 1.15, which means that the wood in the truss can safely resist a 15% increase in its maximum allowable load, as long as the time under this load does not exceed 2 months. Now, for those of you who live in mountainous climates or something like that, you'll know that snow stays on the roof for longer than 2 months at a time. But in general, snow loads are treated as in this 1.15 load duration factor. There's then a 10-minute load duration factor of 1.6, and this is usually applied for seismic and high wind loads. This means that the wood can safely resist its maximum allowable load by 60% as long as that load does not exceed 10 minutes in length. Again, when you think about high wind gusts or seismic activity, that's typically what we're talking about there. So on the truss design drawing, again, the proprietary software will automatically apply the loads during load duration factors once the truss designer selects the loading conditions. Software will then run through all the load combinations and apply the load duration factor associated with the shortest duration load in each combination required by the building code. So using this truss design drawing as an example, you can see that this the combination of the live and dead loads anticipated for this particular truss result in an LDF of 1.15. So that's found here in the first column. Given where this building is going to be built, the wind speed is 115 miles an hour. So you'll see that in the second column at the top. And that yields a load duration factor of 1.6. And then the snow load is set at 30, as you see in the third column, which has a load duration factor of 1.15. So in this instance, in the load combination of dead load and snow load and wind load, the actual stress due to a combination of all three of these loading conditions will be adjusted by the load duration factor of 1.6. So this is a section of the truss design drawing that building designers need to pay close attention to in order to ensure that the correct load duration factors are being applied to the truss given the requirements of the building code and the expectations of the building designer. Certainly, if any of these load duration factors seem to raise any questions, immediately contact the truss designer for clarification. Another important piece of information on the truss design drawing is the repetitive member indication. So each truss is typically part of an overall roof or floor system. And it is common for this indicator to be marked yes. This means that there are trusses on either side of the truss discussed in that particular truss design drawing. They're assumed to share in the distribution of load in the overall system. If we look at the two truss design drawings that we've used as examples so far in this presentation, we can see that here it is marked yes. And again, here it is marked yes. Again, this is pretty common. But when this might be marked no is, let's say, with a girder truss. So here's an example. And this is where the load is not intended to be distributed to trusses on either side of it. Again, in the case of like a girder truss, it's exactly the opposite. Loads are intended to be distributed to it, not away from it. Now, each truss design drawing will also include what building code and version was used in the design of the truss. It may indicate the International Residential Code or the International Building Code or something else like, let's say, the Wisconsin Uniform Dwelling Code. The version of the code being used will be indicated by the year. Again, in most cases, the model codes are adopted on a 3-year cycle, but it typically takes states and local code jurisdictions a while to adopt the newest code cycles. So if we look specifically at, again, the truss design drawings, you can see here at the top, this truss was designed using the 2018 International Residential Code, whereas the truss on the truss design drawing in the middle was designed using the 2021 International Building Code. Now, beyond the code, the truss design drawing will also typically indicate which version of the ANSI TPI 1 standard was used for the truss design. And I cover this in part 1, but I just want to do a quick refresher. TPI 1 is a consensus-based standard that governs the design and manufacturing of metal plate connected wood trusses. The most recent edition of ANSI TPI 1 is 2022. This was approved as an American national standard in December of 2022. So while the version referenced in the 2024 and earlier model codes is the ANSI TPI 1 2014 TPI standard, the new standard will be incorporated into the 2027 model code. I bring this up again in part 2 because I want to draw attention to the fact that TPI 1 reflects the most recent understanding of truss performance in the field. And while it's updated on a different schedule than the building code, it is considered the preeminent document when it comes to truss design. So while the ANSI TPI 1 2014 is the current reference in the model codes, and you can see like in the truss design drawing here at the bottom, it references the 2014 TPI 1 standard. The component manufacturer and truss designer has the freedom to use the newer version of the TPI-1 standard, the 2022 standard. And this is important because there are going to be instances moving forward where updates to TPI-1 may provide more versatile design criteria for particular design application. And there are many instances of that in the 2022 standard. And so it might behoove the truss designer and the component manufacturer to choose to use the newer version of the TPI-1 standard to take advantage of that new design criteria. So as a building designer, it's always good to verify the version of the TPI-1 standard used in the design. And of course, ask questions if you see, let's say the 2022 version listed, and that's outside of what you typically would see and doesn't match your expectation. That opens up a line of communication between the building designer and the component manufacturer to talk about the ways in which the new standard, the 2022 standard, may improve or offer additional options that are either more efficient materially or less expensive to produce, or accomplish a particular framing task more efficiently. Another section of that the building designer is going to want to pay close attention to is the deflection section of the truss design drawing. Now, deflection measures how much the truss will move out of plane when under load, which includes both live and dead loads. Now, generally, for deflection of roof trusses, the deflection in inches due to live load cannot exceed the span of the truss in inches divided by 240. And this will be shown on the truss design drawing as L over 240. For floor trusses, the deflection in inches due to live load shouldn't exceed the span in inches divided by 360, again, shown as L over 360. Just to give you a sense, what this translates to in layman's terms is that if you had, let's say, a roof truss spanning 40 feet, it could have a live load deflection of up to 2 inches. Now, this may or may not be considered satisfactory performance. So often the building designer may specify this design criteria, whether they want anything from L over 480 to L over 180. The smaller this number, the greater the expected stiffness of the truss. This is particularly important, I guess, in floor truss applications, because that's where you typically are trying to limit vibration and increase stiffness, but it certainly isn't limited to that application. Again, the truss designer will input those deflection limits into the design software, and the design will then ensure that the L over deflection remains greater than the specified L over number. So generally, for deflection in floor trusses, the deflection in inches, I'm sorry, hold on. Now the truss design drawing will also list the deflection in inches. So in this case, you see that the truss design drawing, or the truss is designed to have a live load deflection, and vert stands for vertical deflection, of 0.533 inches, so just over half an inch. And it has a total deflection of 1.178 inches. For the building designer, again, it's just important to verify that L over number criteria that was used to ensure that it matches the specifications in the building design. The other thing to look closely at is differential deflection. So this is the deflection that occurs between two adjacent trusses. Again, differential deflection is not going to be noted on individual truss design drawings, but you can view that between subsequent truss design drawings when you look at their placement on a truss placement diagram. So if, for example, the vertical deflection distance between two adjacent trusses, let's say that are spaced 2 feet on center, if the deflection total is significantly different between two adjacent trusses, it may be a good idea to ask questions of the truss manufacturer. But sometimes that differential deflection is something that can easily be dealt with, but other times, it can potentially be missed. So it's always good to look at those deflection numbers and ask questions if, again, that deflection between two adjacent trusses is significant. Another important set of related data is the Combined Stress Index, or CSI. This indicates the combined maximum axial and bending stresses for each component type of the truss. Again, when trusses are loaded, there will be different members will be experiencing axial and bending stresses of varying amounts. And so the combined stress index is an efficient way to measure how those forces are moving through particular webs or cords, or even sections of webs or cords along panel points within the truss. It's a rule of thumb, the closer this value is to 1.0, the more efficiently the wood members are being used in the design of the truss. So as you can see in this truss design drawing, it'll list the CSIs in this fourth column on the right. And the CSI for the top chord, so the TC CSI, is 0.970. It's pretty good. The CSI for the bottom chords is 0.962. And the max CSI for the webs is 0.812. These are all pretty close to 1, so this is an incredibly efficient truss, and the truss designer will get a gold star for designing this particular one. Here's another example. So on this truss design drawing, the CSIs are listed sort of in the middle column. And again, the nomenclature is slightly different. But you see that the top chord CSI is 0.94. Again, that's pretty good. And the bottom chord CSI is 0.90. But the webs are only 0.50, so no gold star for this designer. Now, I'm just kidding about the gold stars, but the lower CSI for webs is actually not uncommon in roof trusses because there are so many other factors at play. But the high CSIs for the top and bottom chords is typically a good indicator that this is an efficient truss design. Again, this is for building designers, it's just a good thing to quickly look at and just sort of see, where those numbers are at. You won't see a number over 1, but if you see a lot that are, again, in the 80s and 90s, that's a pretty efficient truss. Now, we talked about bearing locations in part 1 of this presentation. They're noted typically in the graphical portion of the truss design drawing pretty clearly, as you see in the squares. In this portion of the truss design drawing, their locations help installers and building officials, quickly locate where the trusses are intended to bear. And also, again, in the graphical portion, it provides clues as to how they're intended to rest on those bearing locations, whether it's to be flush to an outside of a wall or centered over a truss joint. Again, the graphical representation is pretty handy when it comes to that. But if you want to get into the performance of the truss, you sort of look at this lower section. So on a lot of truss design drawings, the bearing locations of the truss will be listed under reactions, as you see within this truss design drawing. So they're down here. Here we see that this truss is designed for symmetrical loading conditions. So you can see the 1,677 pounds of reaction into both joint 16, which is here, and joint 12, which again is on the other side. So again, symmetrical loading. If you looked at every other aspect of this truss, you also see that it is symmetrical. Right. Certainly in cases where trusses are symmetrical like this, that makes it pretty easy for installers. But here's another example where this truss is clearly not symmetrical. And so you can see that, again, the reactions are listed in a different location on the truss design drawing, in this case, at this far column at the top. In this truss, you can see that the load conditions differ at the right, the center, and the left bearing locations, with 1,139 pounds, 1,815 pounds, and 795 pounds, designed to go through the truss to each of these respective bearing locations. Now, these reactions are particularly important for framers to pay attention to when installing each truss. Again, in the case of that first truss, because it's symmetrical, when you look at it, and it only has two bearing locations, they may be able to get away with installing that truss backwards. That's not encouraged by any means, but they may be able to get away with it. It definitely doesn't impact the function of the truss. But with that second one, in many cases, the trusses are designed very differently. And so the truss design drawing and the truss placement diagram need to be paid attention to very closely to make sure that those trusses are put in. In some cases, like the one you see on the screen, the truss can look symmetrical. But if you look at the truss design drawing, you can see the reactions are not symmetrical. Close to 1,200 or 12,965 pounds to 13,048 pounds. This doesn't look significant, but again, it underscores the point that there is a right way and a wrong way to install a particular truss. So in this case, this is a girder truss, and the girder truss will have several point loads coming into it. And so it's not uncommon for a girder truss like this to have non-symmetrical reactions at the bearings as a result. Sometimes those reaction numbers will vary significantly more. And so again, it's important to pay attention to. Another thing to look at with regard to bearings is the size of the bearing itself. So going back to the symmetrical truss design drawing under the reactions section, you can see the bearing size is designated as 5.5 inches. Again, that last number 8 being 8/16, so half an inch. And this essentially is a 2x6 wall top plate. Next to that is a minimum bearing area. So in this case, it's 2 10/16 or 5/8 inches. And this is noteworthy, mostly from the standpoint that, let's say, for example, a wall gets a little out of alignment, and that truss heel isn't sitting completely flush to the outside edge of the top plate wall here. The installer on either end may sort of look at that, and when the building inspector comes in, they can both pull out and consult the truss design drawing to look at and measure how much of the truss is sitting on that bearing area to determine whether or not it still will perform as designed. There are other issues, surrounding having a wall that's not, exactly to dimensions, but again, it's underscoring that you don't have to have that full, in this case, 5.5 inches of bearing utilized, that the truss, again, will still perform without problems like fiber crushing and that kind of thing, all the way down to 2 10/16 inches. Obviously, with metal plate connected wood trusses, lumber is an important aspect of the truss design. The truss design drawings will call out what sizes, grades, and species of lumber the various components of the truss are designed with. So looking at this truss design drawing, you'll see lumber called out right underneath the top columns on the left there. Now, the top chords for this truss are designed using 2x4 Doug fir larch north. That particular species is produced in Canada. That's what gives it its north designation. This particular lumber is given a grade of 1800, which is a machine stress rated or MSR grade. If you look at this, the bottom chords and the W5 webs are 2x6 Doug fir larch, 1800. And then the remaining webs are 2x4 Doug fir larch that are visually graded with either the number 1 or number 2 grade. I won't get into all the grading rules and that kind of thing, but again, looking at the grades of the lumber, that might be something that a building designer just wants to quickly glance at to fully understand sort of what is the material that's used in these trusses, and does it raise any questions or produce any red flags. Again, individual component manufacturers vary widely on the number of lumber species, grades, and sizes they typically carry in their production facility. Very large operations may have a lot of room for lumber storage, and so typically, because lumber is a commodity, they'll buy large quantities of a given size and species and grade at any one time. This tends to influence most component manufacturers to limit the number of overall, again, size, grades, and species they carry. But again, something just to pay attention to. As a rule of thumb, the strength properties of visually graded lumber increase as the numbers get smaller. And for MSR graded lumber, typically it has higher strength properties the higher the number it gets. Anywhere from 750 to 2850 here in North America. Here's just another example. So here you can see that all the wood members in this particular truss are designed with 2x4 southern pine, with the only difference really being that the cords are made from number 2 visual grade and the webs are made from number 3 visual grade. This is pretty typical in the component manufacturing industry. Another thing that is going to be identified on the truss design drawing are the compression and tension forces designed to travel through the truss. As you can see just on this little example of sort of how the members in tension and compression will alternate through. This is a pretty simplistic truss design, but like typically how it'll transfer through a design of a truss. So, as you look at this truss design drawing, the forces section down here lists the maximum compression and maximum tension forces for each segment of the truss, grouped by sections of the top chord first, the bottom chords in the middle, and then the webs at the bottom. In this truss design drawing layout or output, when the first number for each one of those sections is larger, that tells you that the segment or member is in tension. And you can see here that if you're really looking at the fine print, the bottom chords sections are all in tension. The top chords are all in compression. When that second number is larger, that segment or member is in tension. And here you can see the bottom chords in the middle are all in tension. And then the webs listed at the bottom, if you look at them really closely, you'll see that they alternate between compression and tension. You'll also notice here at the very bottom that web members 316 and 912 have significant compression forces. Hence, they'll call out, too fast. They'll call out permanent lateral restraints on the truss design drawing. As a reminder from part 1 of this presentation, trusses are designed as essentially two-dimensional structural framing elements. Their ability to resist loads is maximized within the plane of the truss, from the top chords down through the bearing locations. However, when you introduce compression forces like these, the truss designer needs to bring in the three-dimensional nature of the roof or floor system. So, as you can see in this truss design drawing, the forces section lists the maximum compression and maximum tension forces for each segment of the truss. Again, when you look at this, this sort of brings up the need for restraint and bracing. Again, the three-dimensional aspect of the roof. So let's take a look at that. If we spend a minute and talk about sort of truss restraint and bracing, again, each truss element works within a three-dimensional roof or floor system. And while that truss design drawing concerns itself mainly with the elements of the two-dimensional truss, it does incorporate the important three-dimensional element when it comes to restraint and bracing. So there's 3 images here on the screen that show sort of top chord plane bracing at the top, bottom chord plane bracing at the bottom, and web member plane bracing in the middle. And we'll revisit that last image here in a minute. So again, going back to that truss and those high compression forces that we were looking at, we see that, that 316 web and that 912 web are under a high amount of compression. So this could potentially cause significant performance issues. So in order to resist that buckling, permanent restraint and bracing will be called out like this on the truss design drawing. So you'll see webs, 1 row at midpoint, and then it lists the 4 sections or 4 webs that permanent bracing would need to get installed. Again, the point of that is to distribute those compression forces that are going through those particular web members and distribute them to multiple adjacent trusses in the system. Again, going back to that repetitive member that's called out in the other section of the truss design drawing. When the building designer reviews the truss design drawings, it's really good that they review the use and placement of all permanent bracing that's called out like this. Certainly in some applications, I'll use long span trusses as one potential example. Under certain circumstances, a permanent restraint and bracing plan may need to be designed and reviewed by a registered design professional. Again, it's an important thing for building designers to pay close attention to and make sure that when there's those high compression forces, that those are tended to adequately. So as you can see on this truss design drawing, you have 1 permanent restraint called out at 21, and again, another one at 26. To take care of, again, at the midpoint of those 2 web members. And again, you'll see these 2 at the midpoints of these other 2 webs. Beyond that, the truss design drawing will also call out other intended truss restraint and bracing within the system. As you can see here, this truss is designed with the intention that structural wood sheathing will be applied directly to the top chords of the truss, except at the end verticals on the bottom side of the tails of the truss. It's typically where you'd see a return and soffit added. For the bottom chord, it calls out rigid ceiling like gypsum board is to be applied directly. Or of course, there's an option for bracing material to be applied to the bottom chord. Think of like an unfinished garage. Again, you'll see that the web member restraints are called out for the 4 web members to be installed at the midpoints of the webs. Sometimes the truss design drawing will look like this, and you may have notes for bracing that show up at the bottom like this. So there's one on bracing that calls out continuous lateral restraint equally spaced on members when it's called out. And it may also say in lieu of structural panels, purlins can be used as long as they are installed per the instructions on the truss design drawing. Now, then another important aspect of the horizontal restraints called out in the truss design drawings are the diagonal braces that need to be included. So we're revisiting again to this drawing. The truss design drawings won't call out how to apply this diagonal bracing, but fortunately, SBCA publishes a document entitled the Building Component Safety Information Guide, or BCSI. And BCSI is the document that contains the truss industry's best practices on really a wide range of topics pertaining to the handling, installing, restraint, and bracing of trusses. And it includes how to install diagonal bracing. So look at those red members in the box there. And BCSI provides good guidance on how this should be done in conjunction with the permanent restraints within the web member plane that are called out on the truss design drawings. The last section of the truss design drawing that I want to focus on today is the additional notes section. Now, these notes aren't necessarily part of the prescribed data points required by the building code or ANSI TPI 1. And there are too many possible notes to cover all of the myriad of topics that will show up in this section of the truss design drawing. But I do want to take one quick look at least this truss design drawing notes section to just give you an example. So again, if we blow this up, we can see that number one here calls out that unbalanced roof live loads, and I'm going to move to number 4. Unbalanced snow loads have both been considered in the design of that particular truss. Another thing is number 6. This is a very common note that you'll see on truss design drawings. Again, different manufacturers and different proprietary design software outputs will put this designation in different places on the truss design drawing. In this particular one, it was included as a note that indicates the grade of the metal connector plate used in this truss design. Again, in a lot of cases, the gauge of the metal plates will be the same from truss to truss. There are high strength plates, and sometimes component manufacturers may use those for certain applications. And again, that would be called out either in the notes section or again in a different section of the truss design drawing, depending on, again, the software used and the how the component manufacturer sort of uses the notes section. Another example is number 10. Here it says that it indicates that the truss was also designed to accommodate a moving concentrated load of 250 pounds, concurrent with any other live loads, which is it's essentially designed to accommodate workers during the installation process. Again, it's important for building designers to review these notes, not just blow past them, but look at them carefully to ensure that all expected load conditions called out in the building plans are accounted for in the design of the individual trusses, whether that's called out in some of the established sections of the truss design drawing or it's here in the notes. So in conclusion, I want to end with just a few observations. The truss design process primarily concerns itself with the development of 2-dimensional structural framing elements, again, within a 3-dimensional roof or floor system. And by and large, the building designer dictates the overall shape of the truss. It determines the profiles that the truss may fit in. And the building designer may also determine the paths that the loads within that truss will have to flow through the structure, from the peak of the roof down through the foundation. And the truss design drawings, they graphically illustrate each truss in a system for the building designer and for the building official and for the framer to easily, um, inspect it, do a review process, understand how that truss is supposed to function and be installed. But hopefully, this presentation has made it clear that the truss designer has a great deal of latitude in determining exactly where those determined loads are transferred through a particular truss. In this particular presentation, we only covered really a few truss design drawings, so you didn't get a great sense for like the length and breadth of how interesting some of those truss designs and web configurations can get. But with the proprietary design software that component manufacturers and truss designers have at their fingertips today, it's really incredibly powerful, and it gives component manufacturers the ability to offer a wide variety of solutions to their customers for really any framing problem they see. So this means that, component manufacturers have the opportunity to help building designers and builders and developers save money and materials, reduce construction cycle times, reduce waste, and really accomplish a lot of, or address a lot of pain points that currently exist in the construction industry. Now, as this presentation really tried to draw attention to, is it's important for the building designer to thoroughly review truss design drawings to ensure that the truss designer, in all of their creativity, has met all the expected architectural and engineering-based expectations that were in the building plans as they designed those particular trusses. Well, maybe wasn't clear, but I do want to make clear at the end of this presentation is just that, the key here is, to ensure that those expectations are met of the building designer. The truss designer, because they have this great opportunity for creativity, the earlier that they're able to interact and interface with the building designer to find and work together to find and explore sort of the wide range of possibilities and how to address a particular framing challenge, the better off that overall project will be, and the more time, money, or materials will be saved as a result.